we go. We're recording. Hit continue. There we go. Okay. So like I said, if you have a chance, please print off the missing square puzzle. It's kind of a neat activity. I had to change some of the activities for this course because it's online. So this is one of the ones I changed. So if you have printed it off, what I want you to do, for those that are still printing, I want you to cut out those 4 top shapes, the 2 triangles and the 2 rectangles with pieces missing. Polygons, I guess we just call them polygons, right? I want you to print those off. Sorry, cut those out. I don't know if you've ever seen this puzzle. It's actually kind of fun.
Brian.
Alice.
I accidentally printed it on both sides. Should I print the second page again?
Yeah, you can do whatever you want. Just print it. I mean, if you print it on both sides, all you need to do, well, you can still do the step 2. Like you don't have to print it off again because you're just going to cut those out. Basically, what it is, we just need this triangle, this big square at the bottom here, and I'll explain that. But yeah, you just cut out the 4 pieces. You don't need to print it again. It's fine.
Okay, because I saw it was part 2. Also.
No, it's fine. I can explain it or I can leave it on the screen. So.
Okay.
Don't need to waste paper. You know what they say? Paper doesn't grow on tree. Wait, that can't be right. Paper doesn't grow on trees? Wait. I just want to give you a couple of minutes so everybody can get it printed off if they can and or cut out. It would have been nice to find an interactive one of these puzzles, but I couldn't find one. Let me look again. Oops. Interactive missing square puzzle. Interactive missing square puzzle. Let's see if I can find one again.
I've seen someone use one in Google Docs, like the collaborative Google
Docs.
Docs.
Oh yeah, that would have worked in Google Docs. Yeah.
I can't remember where they got it though.
I thought somebody would have had a Java applet or like just something like that. Easy. Missing square. Gather your materials. No, that's just how to do it. Actually, I think that's where I got this one from. Pinterest. I'm not going to Pinterest. Oh my goodness. Sorry for those that like Pinterest. I sure don't. Oh, that's not the one there either. Okay, I'll put that back there. Janelle Hool doing attendance as I do this. Okay, so for those that have printed it off, and if not, I'll link you a website kind of shows it. What you want to do is you want to basically take these 4 shapes at the top, the 2 triangles and the 2 other polygons, and you want to put it on this piece of paper here down the bottom so that it fills up the whole area. Nothing's left blank of the green shaded part, right? So there's no extra little squares there or anything. So you should be able to put those 2 together, and I'll give you a hint. The triangles go on the top and then the other ones go on the bottom, right? So put those on the piece of paper so that the whole green shaded area is filled. And if you printed it off at home, then you don't know that it's green because you probably printed in black and white, but you can see on the diagram there. So take a minute and do that. Wow, we are missing a lot today. I don't think it's optional Thursday. I don't think that exists. Okay. Did anybody was anybody able to put all the pieces on there so it fills up the whole green area? Eric was?
I'm still cutting mine out.
Okay.
What's
Oh,
the
sorry,
lid
sorry,
tag?
Callie. Lacey was. Sorry, what was that, Alice?
Can you scroll down? I want to see the polygons again. I'm wondering if
Those ones there?
yes, I just have a lid slit left, unless I cut them out wrong. Did
Well, if
see
you printed it off and cut it, then it should be fine. So you have a little piece left. Well, it normally fills it up pretty good, but I want to. It's a missing square is what's going to happen in a sec. Okay, so I'll just keep talking. I know some people are still cutting. That was to like fill up the whole thing. Now, what you want to do is you want to try to do the same thing again. But my recommendation is where your two triangles are, reverse them. Okay. And basically I want you to rearrange it so it fills up the area, but what you're going to be left with is one empty square. Okay. So rearrange those, and preferably probably the triangles is what you're going to rearrange, and see if you end up, this is part 2, by the way. So you can still do it on that same picture above, right? Because they look the same. Rearrange them so to see if you can get an empty square someplace in there. So Brandy, you got it. You got an empty square, eh?
Yeah.
Okay. Well, how explain that to me, how it's possible, because one way you put it on there, they fill them all up, but the other way, just by moving, I think moving the two triangles, I don't know what else you had to move, and you ended up with a blank square. Is it magic?
It's hard to explain.
There is tons of math stuff out there that's like this, that you can, and this would be a great activity. You can give this to of kids from early on. You might have to cut it out for them, right? But later on, you might get them to actually print this off and cut it out and do it. And it's kind of a neat, well, I guess trick is kind of the word.
I'm trying to wrap my head around how this is mathematically possible, because I also
you and many people will be wrapping their head around how it's mathematically possible or impossible.
I mean, logically speaking, it's still the same area.
It's still the same area. Why would it be any different, right?
Wait, what are we supposed to do?
So you cut out your 4 figures there, Callie.
Yeah.
Okay, put them on the green shaded area, so all the green shaded area is filled. That was step 1.
Step 1.
Let me know when you got that. And again, I think you have to turn. Sorry, go ahead.
I'm getting the. Oh, okay. Never mind. I figured out both of them.
Okay, so one way you do it and it fills up the entire green thing, right? And then you
Yeah.
rearrange something and it, all of a sudden you have a blank piece to it, right?
Yeah.
Okay, so I mean, let's go back, and I think I have some here. Well, here's a good. Well, here, let me look at images. Let's grab an image here for those that aren't seeing it. So here's a good image here. Boop. You can see on this one here, right? All we did, well, you can see it's rearranged too, but the triangles are rearranged, but then the bottom two are rearranged also, but you still get the same, looks exactly the same. This missing square puzzle has been around for actually quite a while. Like if you go onto the, well, you go onto the internet and you'll find tons and tons of stuff related to it. Where we are here, all missing square transom. This is here. So here's a good example of it here. You can see base 13 units, height 5 units, right? Why is there one missing square arrangement? Well, figure that out. I'm not going to give you the answer. And if you look, there's lots of, you can go to YouTube. We can watch it on YouTube, right? I think this is where I got it. KiwiCo, I think that's where I got this one, right?
Isn't this the same thing? Like, I remember I was seeing, I think it was on Facebook or a video on YouTube, and it's like they cut up this bar and then they cut that bar a specific way so they had one little piece left, but the bar was like the same size.
Yeah. You'll often see it. I think they call it the chocolate bar puzzle too, where they cut a chocolate bar up into pieces and all of a sudden there's a piece left over of chocolate bar and we're like, what the heck, where did that come from? Right?
Yeah, that's what I'm talking about.
Oh yeah, okay. They also do, there's also a puzzle out there with money, and it has to do with a number of people giving them money and it all divvies up and all of a sudden it just doesn't work, right? There's something weird about it, right? So this one, I mean, this Kiwi company, you can look at the missing square puzzle. So you can print off that. You can actually cut out the pieces. It'd be really nice if you did this at school and you had a color printer, right? Then you could really, for the kids, set it up for them. This would be a great, this puzzle would keep them busy for quite a while, but it's also
Fun,
teaching
though.
something. Sorry, what was that, Alice?
It's fun and it teaches them strategy.
Oh, okay. And again, you can look over the internet. There's lots of stuff over the internet there for stuff like that. So, oh, hang on. Let me grab attendance here. Some other people joined us here. Lori. Who else is it? Kyle. Oh, where's Kyle?
Hey,
Right.
yeah.
There you go. There's Kyle. Okay. And Terrence. There we go. Sorry, I'm just double checking attendance as they pop up here. Okay, so that's the missing square puzzle. So like I said, right, it's on, if you want to use it, by all means use it. Use it with your class, whatever you want. So if there's, again, missing square puzzle, you can print off exactly that, cut them out and show it. Okay, so you can see what we're doing today. We are doing chapter 10. So this is where I said before, right? And if you guys are forgetting or wondering what we do every day, well, it's all there, but I also post every day right on the math blog, day 16, contemporary math, like what we're going to cover today, right? Just as a short little blurb of what we're doing. But if you're ever trying to remember where everything is, it's all here. Course materials at the beginning, right? And then all the day-to-day stuff. It will tell you exactly what we're doing. So if you happen, let's hopefully not, let's say you're missing a day, right? You know what we're going to cover. And then the next day, for instance, like what we did on Tuesday, I will put the Zoom video up there. And I watched a bit of it the other day. They are boring. That's me talking and it's boring. Oh my goodness. So I feel bad for you guys sometimes. Okay, so you need your formula sheets today because we are going to be using, if you look on here, I even put it on here, formula sheets. We're going to be using all this stuff here, area, volume, a little bit of the conversion stuff too. Okay. But mainly these ones. These are, I know it's a kind of a poor copy. I've been using this one for years in all my classes. It's a really, really good formula sheet, as in the formulas are really simple. There's nothing weird about them. They're pretty simple. Okay. So that's that one there. So let's, oops. I think I got everybody now. I'll check attendance in a minute. Okay, let me open up PowerPoint 10 here. Here we go. So we're breaking this one up today we're breaking it up into 10.1 to 10.3. Then we'll do some questions, and then 10.4, 10.5, and then we'll do some questions. Just so you get a break, because it's it's a longer chapter in this game. Yesterday was short, today is longer. Let me move that a little smaller on my screen there. There we go. Okay, the measurement process. So the measurement process is, we can talk about different properties of it. So the main ones that you guys use all the time, right? You want to choose the property, length, area, volume, whatever. Select the unit of measurement. So for instance, you either select imperial or metric, which we're going to talk about. Compare the size of the object with the size of the unit. So that would be like using a ruler and then measuring something out. And then express the measurement in a number with units. And that's the biggest thing that a lot of people forget. And you'll find this with students, always forget the units. Well, it's a very, very important thing. And I'll tell you an example why in a minute. It's actually a story about NASA, which is actually quite interesting. I think it's interesting. Okay. So when you're doing measurement, one of the main things you have to do is you got to talk about approximation, right? Because when we're doing stuff and we don't have access to, let's say, a ruler or a measuring tape or something like that, or a scale, sometimes you have to use approximation. Now, some of the earliest forms of approximation were your foot, right? Which we still use today. If you want to measure something, have any of you ever gone toe to heel, toe, heel, all the way along to measure something to get an approximation in the number of feet? You ever do that? Yeah, it's super common, right? If you use your thumb, the width of your thumb is approximately an inch, right? Your fingernail is approximately 1 centimeter, right? If anybody has horses, how do you measure the height of a horse? Hands, you measure it in hands, right? It's distance, yeah, you measure it in hands. It's a very common measurement for horses. The other one is yard, right? And normally a yard, and this is actually, when you want to get back to the imperial system, it was the King of England at the time. That's what it was. In England, if you wanted to measure a yard, it was the distance from the king's nose to his middle finger, like the farthest finger out. That was a yard. Well, the problem was in Britain or in England at the time, kings would come and go, so the yard would change. It's true, that's how they actually measured stuff. So when they did that, they actually had to standardize what stuff was. And the US, which is, I mean, it's a big country, it still uses the imperial system, but the original imperial system was English. It was from England, okay? So the US system is also known as the English system because that's where it comes from, right? This is, and the weird thing is in Canada, most of you probably know imperial and metric kind of back and forth, depending on what you want to know. So for instance, if I asked you what your height was, you would tell me in feet and inches, right? If you were telling me the distance from someplace on the highway, you might use kilometers. Or if you're out in the country, you'd use mile roads, right? It really depends on the situation, right?
Or minute.
Sorry, what?
I always tell people it's like, 10 minutes from there.
10 minutes. Yeah, and it's based on,
Yeah,
and normally it would
that's
be based
something-
on a speed that you're traveling at, right?
Yeah, that normally mixes Americans up though. They're used to miles, and while kilometers convert quite nicely into minutes, miles do.
Yeah, and again, it's, you think about even all of Canada, right? All of Canada is divided up into miles. Hey, you've told people go 6 miles north and then 2 miles east, right? It's the mile roads, right? When you're out in the country, that's super common. But 99% of the world uses the metric system. It's only the US and 2 other tiny little countries that use it, right? So some common measurements, and you probably know most of these anyways, right? Yeah, learning the system requires extensive memorization. Okay, standard one, 12 inches in a foot, right? 3 feet in a yard. These 2 measurements, you probably don't use this one very much anymore. 16.5 feet in a rod. Still used in farming, actually, though. This one, where is this one used? Where have you seen that word before?
It's a nautical term.
Furlong? No, knot is like depth is usually a nautical term. Furlong is
sorry, fathoms is what I
fathoms.
was
Yeah,
thinking.
you're right. That's that close. Furlong, you probably heard in horse racing. They'll say like 2 furlongs or 2.5 furlongs, right? It's measured in that way. And then the last one, which we always often know, mile, right? 5,280 feet in a mile, right? These are common conversions, right? Now, do you have to memorize these? No. Are they on the formula sheet? Yes. Okay, so then we can talk about this is still within the imperial. We'll get to the metric in a sec. Within the imperial, we can talk about length, area, volume, right? So for instance, you could have a unit of area. 1 foot by 1 foot is 1 square foot, right? Now you could also take that foot and break it down into inches, right? 1 foot is 12 inches, another foot is 12 inches. So you could break it down into 12 inches by 12 inches. So there's our conversion, right? 1 square foot is exactly the same as 144 square inches. And you can see it visually that they're the exact same thing. Okay. You could do this with yards, right? 1 yard by 1 yard. Okay. You could break that down into feet, right? 1 yard is 3 feet. Oops, why didn't that work? There it goes. So 3 feet, right? 3 feet by 3 feet. So 1 yard is 1 square yard is exactly the same as 9 square feet. Okay. And you would see this today, like if you went down to Home Depot or some place where you could buy like an area rug to throw on the ground, they usually measure it still in square feet. It's not often they'll measure it in meters. Okay, so that's area, two different areas. Now, the next one would be volume, right? Volume is 3-dimensional. So 1 foot by 1 foot by 1 foot, cubic feet, right? Cubic feet. So that could be broken down into inches. So 12 inches by 12 inches by 12 inches. Whoa, that's a lot, right? So again, 1 cubic foot is exactly the same as 1,728 cubic inches. Now, there's a good example. Cubic inches. Where have you seen that before? Or heard that before? Where have you heard of cubic inches before?
Math.
No, thank you. Oh, come on. Math. In the real world.
Building.
What did you say?
Building houses.
Cubic inch. Well, you won't see cubic inches maybe too much in building a house. You might see maybe for insulation, you might see it for cubic inches or cubic feet. Here, I'll give you an example. It's an audio clue. Vroom, 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 vroom.
Oh, for engine size.
There we go. And in particular, when they talk about cubic inches, I'm talking about the old muscle cars, right? You know, the big, right? The ones that go, you know, when they're idling along there, right? They'll be in cubic inches. The same with Harley motorcycle engines will be in cubic inches. Now, that's a little different than modern day cars, because modern day cars, they don't talk about cubic inches, they talk about metric.
Cubic meters?
No, liters, right? Oh, I got in fact, Mustang, the 1985 Mustang came out, was a 5-liter engine. They measured it instead of cubic inches, they measured it in liters. Same thing, right? But one's in metric and one's in imperial. We'll talk about that. But that's a good example of right there, cubic inches that we still use nowadays, even though we are in a metric system.
They do that with trucks though too, don't they? Like 5.9 and
5.9, like any of the Cummins diesels, right? They always measure them as 5.9, 6.5, whatever it happens to be, liters, right? So they do use metric. Okay, so that is volume. Now, this next one, if any of you have ever got dirt, gravel, sand, any of that delivered in a dump truck, they often will give you a yard of soil. Have you ever heard that? You buy 5 cubic yards of soil. Has anybody ever heard that before? Well, maybe not. Okay. Well, that's how they normally do it, right? So a cubic yard, and you can see it right here, is 1 yard by 1 yard by 1 yard of whatever it happens to be, rocks, sand, soil, whatever it was. And you can break that down break it down into feet, 27 cubic feet, right? So for instance, if you wanted to kind of figure out, let's say you're putting dirt in your yard or sand in your yard or gravel someplace on a road, and you wanted to figure out how much you needed. Well, 1 cubic yard is kind of difficult to do, but look at this, right? These are feet. If I broke this, it's like a Rubik's Cube, right? It's like a Rubik's Cube. I could take the top layer off and the middle layer off and lay them down, right? I could figure out what my length is and my width is, right? So it'd be 3 by 3. So it'd be 9 feet long by 3 feet wide by 1 foot tall. That is still a cubic yard. Doesn't make any difference, right? So people will use that conversion when they want to order gravel or something like that, or dirt or sand. Okay. Now, we also use the imperial system a lot in cooking. Okay. So most times the recipes will say 3 teaspoons, right? Is that right? 3 teaspoons equal 1 tablespoon? Yeah, that's right. Took me a tablespoon, half a fluid ounce, right? Ounces, tablespoons, cups, quarts, gallons, right? All those are imperial terms that we use all the time, right? If you have ever baked bread and it says use 4 cups of flour, 3 cups of flour, half a cup of sugar, teaspoon of salt, right? You're using imperial. So those are capacity, right? So the imperial system, it's outdated, it's old, but we still use it. In fact, if you go to buy a piece of lumber, you buy a 4 by 8 sheet of plywood, a 2 by 4 is still, well, it's not technically 2 inches by 4 inches. It's less than that, but that's what it's originally called. Okay. Now, is there a better system out there?
Metric is much easier
metric.
to understand.
The metric, the nice thing about the metric system, or the Système International, right? If you want to actually get the French based on it, right? It's called the SI system. It's the metric system, right? It is base 10. Everything is just a matter of adding zeros or moving the decimal. That's all it is, right? And I mean, we talk about this. We'll talk about some of the units in a sec, right? So everything's base 10, but just what we did before, right? We have length, area, volume, or weight, right? Instead of inches, yards, right? Or square feet or square yards, or cubic inches or cubic feet or ounces and all that stuff. We have it in the metric system would be stuff like this, right? Meters, meters squared, kilometers squared. Volume is centimeters cubed, meters cubed, liters. Weight, kilograms or grams. Now, here's something interesting, and this kind of blows me away. We were just talking about engines and vehicles, right? Remember cubic inches? And some of the newer vehicles are measured in liters. What about motorcycles?
They're cubic centimeters.
Otherwise known as cc's, aren't they?
Yep.
Right, you say, I have well, in fact, I have a motorcycle that's a 1300 cc engine, right? Which is technically 1.3 liters, right? So you can do the conversion there. Whereas opposed to the Harley Davidsons, right? You'll see right on the side, they'll say 80 cubic inches. That's the 80 engine, right? Is an 80 cubic inches. So some, because they're American made, right? Some things are used back and forth. But you'll see here, volume, cc's, cubic centimeter, right? We often talk about that. Or you see it on medical shows, right? Give them 50 cc's of adrenaline. Well, that would be a lot of adrenaline, sorry. Whatever it is, they give them adrenaline, right? And then weight, grams and kilograms. Those are the common ones. Now, so here's the big one here, big chart here. You can kind of see this. And this is, if you want to break down, if you actually look at here, 10 to the negative 6, well, micro's way up there, but these all work, right? 10 to the negative 3, negative 2, negative 1, 0, 1, 2, 3, right? That's our prefix for whatever our factor is, right? So centimeters, right? There is 10 centimeters in a decimeter, right? Then there's 10 decimeters in a meter, right? And you can just keep working your way through all the so it's just a matter of moving the a decimal place in this case. And you can see some of the more common symbols, right? K, H, and then we put whatever is behind it, like km, kilometer, right? hectometer, decameter, decimeter, centimeter, millimeter, micrometer, right? Meter is our basic one that we use all the time. Okay, now let's see if you remember any of this stuff. Okay, I got 3 conversions on the screen there. Millimeters to meters, centimeters to millimeters, and meters to kilometers. You probably do not need a calculator because all you're going to be doing is moving the decimal place. Give it a shot, see what you can do. Now I'm going to double check attendance while you're doing that because that shouldn't take very long. Where's my oh, there's Laurie Martin. Okay, somebody want to give me an answer here? What's the first one? Millimeters to meters.
Is it 1.495 meters?
Yep, because there's 1,000, right? There's 1,000 millimeters in a meter. So there's 3 zeros, so you would move it 3 decimal places. Correct. 1.495. What about centimeters to millimeters?
295.
You got it, because there is 100 centimeters in a, no, sorry, let me do that again. There is 10 millimeters in a centimeter, and we're going larger, right? So then we're gonna move it there to 295. Okay, what about 38.741 meters? What's that in kilometers?
.0387.
0.03. Yes, yeah, there we go. Yeah, we move it 3 spots, right? Because there is 1,000 meters in a kilometer. So then we move it over 3 spots. Excellent. That's the nice thing about the metric system. It's just a matter of moving things. Okay, now what I want you to do here is there is 6 items. Okay, and I want you to estimate what measurement goes with what thing, like a nickel, like I'm talking about a nickel, like a 5-cent coin, right? 2-liter bottle of soda, like 2-liter, compact automobile, your daily allowance of B6, size D battery, right? The big batteries, and a large watermelon. Try to figure out which one goes with which. Take a minute to do that. Well, less than a minute, probably takes about 30 seconds. What am I missing here? Okay. All right, let's do this. Nickel, which one's a nickel?
5 grams.
I would say so. 5 grams. Compact. Whoop. Back up. You saw it, right? Well, compact automobile. Sorry, I screwed that up. 1,200 kg. What about a 2-liter bottle of soda?
2 kg.
2 kg? Yeah. Recommended daily allowance of vitamin B6?
2 milligrams.
Yeah, everything. Normally when you talk about pills, anything to do with pills are always milligrams, right? Size D battery.
100
Marco?
grams.
100 grams, yeah. And a large watermelon,
9 kg.
9 kg, yeah. Some of those good Texas watermelons, if anybody's ever had them. Again, it's interesting. Estimation is one of those things that when you teach this and when you actually have to teach it to kids, some of the kids will be really good at estimation, some will not have a clue. What is a large watermelon weight? 1,200 kilograms. I'm like, okay, no, that's a really big watermelon, but okay, thanks for playing. Okay, now, the other two that we have to deal with, metric and imperial, really, really common is temperature, right? Fahrenheit is imperial, right? And the stuff we use all the time, Celsius, is in metric. Now, here's the interesting thing. When people talk about the temperature in their house, most times they'll talk about it in Fahrenheit. Yeah? What's the temperature of the house? 82 degrees Fahrenheit. A lot of people do that. But when you actually talk about temperature outside, we use Celsius all the time, don't we? Oh, what was it today? Oh, it's plus 15 today. It's negative 40, whatever it is. But most of the time we use Celsius. When you're baking or cooking, most times you use Fahrenheit. Yeah? Yeah. Now, do you guys know the conversions back and forth? Well, here they are. If you want to convert to Celsius, you take the Fahrenheit, subtract 32 times by 100, divide by 180. Okay? If you want Fahrenheit, you take 180 over 100, times it by the Celsius, and add 32. Trivia time. Where do Celsius and Fahrenheit meet? Where are they exactly the same? There's a temperature.
The minus 40.
You got it. It's minus 40. Right? So when we talk about minus 40 Fahrenheit and minus 40 Celsius, they're the exact same point, right? So if we drew this on a graph, you'd have two lines, and where they cross is at minus 40.
I was going to say that these formulas look familiar, but I recall them being 5 over 8 and 8 over 5. Instead
Yeah,
of
it's the
100
same
over-
thing. But all you're doing is reducing the fraction down. Right, you'll see them like that. They're often reduced. You could actually use it as a decimal if you wanted to. Also, there's these ones. There's variations on that formula, right? Yeah, 5/8 is the one you're talking about. Yeah, or 8 over 5. Yeah, 8 over 5. 5/8.
So what's the significance here of the 100 and the 180?
It's just another way to calculate it. That's the way the US calculates it a lot of the time. I learned it as the way you learned it, as 5/8 and 8/5. I think that's what it is, right? I think these are a little more accurate is what it is. It wasn't 5/8. I can't remember. Anyways. Okay. That's temperature. Okay, now, next one. You get questions like this. Cheetah can run, cheetah I think it is still the fastest animal on the earth, 60 miles per hour. So what is this in feet per second? Oh my goodness. This is a typical question you would get when you're doing conversions. This one's all imperial. So what you can do is you can do it in multiple steps if you want. You can convert 60 miles to feet, right? And you convert hours to seconds if you want. That's probably the easiest way, but here, let me break it down here. So, oops, 60 miles per hour. So how many feet are in a mile? 5,280, right? How many minutes are in an hour? 60 minutes. And then how many seconds are in a minute? 60 seconds. So if you look at what we're doing here, we're taking 60, multiplying it by that, and dividing it by both these numbers here. So I'll show you the breakdown here. Wow, you can see all the breakdowns. So 60 times 5,280, and then 60 times 60 on the bottom. And if you do the math, you figure out that this sucker moves. Now think about how fast this actually is. 88 feet a second. So look at where you are sitting right now and try to see something that's 88 feet away. You might have to look out a window to find it. And you think about how fast a cheetah runs. In 1 second, they've covered that distance. So the point I'm getting is don't try to outrun a cheetah because you'll be lunch if you do. If you try, okay?
Can't even picture myself trying.
I can't even imagine. 88 feet per second. That is wickedly fast. Okay, So now that we've talked kind of about a little bit about metric and imperial, what we can do is we can start using those things to do calculations, and calculations that you'll probably use sometime in your life, maybe every day. We're going to talk about area of different shapes. That's what we're going to start with. Perimeter, and then I think after we do some questions, we're going to talk about volume. Okay, so let's do a little background on area. So area and perimeter. The area. Why is this in? Sorry, it's on my screen here. Hang on. Let me. Sorry, my chat window got in right in the middle of my screen there. So let R be the region and assume that a unit of area is chosen. So what we're talking about here is we're talking about units of area. Could be in inches, could be in feet, could be in meters, could be in centimeters. Who cares? So you're trying to cover, and you think about this with area, you're trying to cover the whole thing without any overlap. That's our basic definition of area, right? And normally when we talk about that, usually squares are chosen to define a unit of area. Like if you took, for instance, like I'm looking right now at my floor in my classroom, it's tiles, square tiles, and I could count up all these tiles and that would tell me the area in square feet of this classroom, right? Normally that's the common one, squares, right? If you talk about carpet, it's in square feet, right? Or square yards, right? Now, if you got a large amount of carpet, right? If you have two areas, this area and this area, that are the same, they are congruent, right? If it says this area is the same as this area, even though the shape could be different, right? So for instance, here's a good example. If you look at the screen here, there's a rectangle. Could we figure out the area of that? Yeah. Look at this. If I turn it sideways, it's now a different looking rectangle, but they are congruent because the area is still the same, right? It hasn't changed, right? And the interesting thing is you can cut out pieces of this, move them around, and you'll still have the same area. Okay, so then that gets us to what's called the addition property of area. So if you have an area and you cut it up into chunks, right, that don't overlap, then the area is still the same. A good example of that is the opening activity we did, right? We could figure out the area of that big triangle, rearrange it all, the area is still the same, even though they're moved around, and that's the addition property. But that one's also a trick, but you have to figure that one out if you want. Okay, so let's start with some basic area, and this is where you'll have formulas to work on this. Area of a rectangle, length times width. It is on your formula sheet, right? And all you do, and it doesn't matter because length and width are interchangeable. When you multiply, who cares? Length and width. That's the area of a rectangle. And it's in square, whatever it happens to be. Parallelogram. Parallelogram, the formula actually looks very much length times width, but we have a slightly different shape. This one on the left is our parallelogram, right? If we cut this piece off and stuck it over here, well, look what we have. We have our rectangle. So instead of length times width, it's base times height. Okay? Base times height. Now, one of the biggest things that they do in any question with area or volume is sometimes they give you more information than you need. Okay? So look at the formula here. We need base and height. Okay? So look here. I see 3 measurements on this parallelogram. Do I need all 3?
No.
No, I only need 2. I need the base, which is
10.
10, and I need the overall height here, not the slant height, but the height of 4, right? So if we look at this, the base is 10, the height is 4, so the area is 10 times 4 or 40 centimeters square. Super common to get more information that you need in a question. Okay? Here's another parallelogram. Let's take a look at this one. Still a parallelogram. Look at this one. We got 4 measurements on here. Oh boy. What are the only 2 we need?
3 and 12.
The 3 and the 12, right? Because we need the base, which is 3. We need the height, which is 12. 3 times 12 gives us our 36 square centimeters. Or centimeters square. Doesn't matter how you say them. Okay, that's parallelogram. Okay, triangles. Triangles is half the base times the height. Because I'll show you an example here. If we do this, if we have a triangle and we cut this piece off here, We stick it up here. Oh my goodness, that's a parallelogram, right? So we need half the base times the height. Okay, so let's look at an example here. Here's more information than you need. I want the base and I want the height. What's my base? What's my base?
14.
Nope.
10.
10. What's my height?
7.
7. So half. So 10 times 7 is 70. Half of that is 35 centimeters squared. Okay. And again, do you have to memorize these formulas? No. Are they on your formula sheet? Yes. Do you have to know how to use them? Of course. Okay. And your units. Trapezoid. Trapezoid is a fancy formula. A plus B, which is the top length and the bottom length added together, multiplied by the height, and take half of that. I think on the formula sheet, it's written out slightly different than that, but it's still the same thing. I think it's A, what is it on the formula sheet? A plus B divided by 2, is that what it is? Hang on, I gotta look. I didn't want to do that. Hang on, sorry. Formula sheet.
That's exactly the same, isn't it? Half A plus B.
Oh, it is. Okay, yeah, it is. I wasn't sure if it was or not. Sometimes sometimes look, for instance, see that, look at the formula sheet here. You see the area here, let me zoom this in here. The area of the triangle, you see how it's half times base times height. Sometimes you'll see it written as base times height with it over top of a 2. So base times height divided by 2. Same thing. Multiplying by a half is exactly the same as dividing by 2. So you'll sometimes see it written slightly different. Whoa, that's getting a little, whoa, hang on, sorry. There we go. All right, let's go back to this. From current slide, sorry. So there is, okay, I don't have an example for this. Okay, that's area. What's perimeter?
Length plus width, is it?
Say that again.
Length plus width, or 2 lengths plus 2 width?
2 lengths plus 2 width, yes.
Oh, if you're talking, that's of a rectangle. But what I'm talking about is the basic definition of perimeter.
Distance all the way around.
Distance all the way around. Now, when it's interesting, when I explain this to kids in Brandon, right? And this will be different for you guys, depends if you've been to Winnipeg or not. When I talk to kids in Brandon, I'll say, okay, have you ever been to Winnipeg? And they'll go, yeah, I've been to Winnipeg. I said, is there a highway that goes right around Winnipeg? Yeah. It's called the, what kind of highway is it? It's called the
Perimeter.
Perimeter Highway. Now, here's the deal. Some of you might have kids that have never been to Winnipeg, right? If you're really quite a ways up north, some of them may have never been to Winnipeg. They might not know what the Perimeter Highway is. So you probably can't use that explanation when you're describing perimeter. You always got to know your audience when you're teaching things, right? And I'll give you an example. This is a great example. Grade 12 provincial exam. It was an English exam, and the concept was talking about the metro. The metro is like a railway system within a city. Anybody that was from a city or had some experience knew exactly what that was, but many of the rural kids had no clue what they were talking about. It was a mistake on the provincial exam because they didn't know their audience properly, right? They were using a word that some people might not know. Good lesson in teaching, by the way, know your audience. Okay, so in this case, if you're trying to explain perimeter, you would just say the distance around something. Here's what I talk about. If I'm in a classroom, right? And if I'm in the classroom, I could look down and I could say, okay, kids, I want to replace the tiles on the floor. Well, that's area. What if I wanted to replace the baseboards, right? The baseboards are the things that go all the way around the perimeter of the room. You can explain that to them. Hey, what if I wanted to fill this room with water? What would I be talking about then? Perimeter, area, and then filling it the whole thing with water would be volume. Yeah, we're gonna do those coming up in a bit, but you always gotta have to explain things to some people. Okay, so perimeter is a length measurement around it. Okay, so now perimeter, you just measure it. Now there are some special perimeters. really special perimeters. And they're the ones for circles. The perimeter around a circle has a different name. It's called
Circumference.
circumference. If you get a chance and you get to teach this, there are some really good books out there. And you might have heard them before. They're called Circumference and the Knights of Pi, I think is what it's called. Give me one sec here. Oops, let me back up here. I want to show you this because when I've taught this in class, I get everybody to bring an object into class, and it's really a neat experiment. Let me find it here. What is it? Circumference and circumference and the Dragon of Pi. Here it is here. So his name is Circumference. His wife is Lady of Diameter, like Lady Di, right? And their son's name is Radius. I don't know why you would want to call your kid Radius, but anyways, right? So what it is it explains the whole concept of circumference and how it's related to pi. Okay. It's a really neat book if you can get it to do it. One of the best experiments you can do, and I can find it someplace and put it on the webpage if you want, is you get people to bring in round objects, any round object you want, right? And what you do is they measure the distance around an object. So I got a cup here. I could measure the distance around that object, which is the circumference. Then I could also measure the distance across the circle. What's that called when you measure the distance across the circle?
Pi.
Diameter.
Diameter, right? It's a really common thing. Circumference is the distance around, the diameter is the distance across. If you measure those two things on any circular object and divide them, circumference divided by diameter, you get some magic number, and that magic number is
Pi.
it's pi. That's where pi comes from. A lot of people don't have a clue where pi comes from. It's circumference divided by diameter. It's as simple as that. And you try that experiment in your classroom when you get a chance. Write it down so you don't forget. Do something and start by reading the Circumference and the Knights of the Round Table, right? Knights of Pi or whatever it is. So there's the formula there. Circumference divided by diameter is pi, or circumference is pi times the diameter. Really common. Okay. So let's look at an example here. So the equatorial diameter of the Earth, right, is 7,926 miles. So the diameter across the Earth, and it's not a perfect circle, right? It's actually squished. Calculate the distance around the Earth at the equator. Now, when we use pi, right, we can use different numbers. The most common is 3.14, but you can also go to 2 more decimal places, right, like this. Okay. So how do you find the circumference? What was the formula? Circumference is pi times the diameter, right? Pi times the diameter. So grab your calculator and do the first one for me. 3.14 times 7926. And then just write it down. Or I'm going to put it on the screen in a sec. So. Okay, you get a big number. I'll put it on here right away. You get 24,887.64 miles. Okay, now do the same calculation again, but instead of 3.14, use 3.1416. So we're going to 2 more decimal places. You do that calculation. Once you do it, and I'll put it up here in a sec, you get 24,900.322. What the heck? So the Earth is changing size? Why is the Earth changing size in circumference?
No, it's just that our definition of one of the variables changes.
Basically, when we're talking about pi, right? If we talk about those 2 extra decimal places, does it make a difference? Yeah, in this case, it makes a difference of about 12.7 miles, right? Just based on approximations. So is accuracy important when you're doing math?
Absolutely.
Absolutely. So here's my example that I was going to talk about before. So there is a, I don't know if you've read in the news, they've been sending a lot of stuff to Mars over the last, 20 years, right? So the different countries are now sending stuff. Did you guys ever read about or hear about the Mars mission, and I'm not talking about the movie with the guy that gets stuck on Mars. I'm not talking about that movie. Do you ever hear about the Mars mission where they screwed up?
Yep.
Oh, you know this one about the difference between kilometers and miles? So there was a massive,
Yeah.
oh, sorry, go ahead.
Yeah, I didn't know it was kilometers and miles, but I remember that one of the computers was in Imperial a while back home. It was in metric or something like that.
So what had happened is it was calculating the difference between imperial and metric, miles and kilometers, and it did a miscalculation on fuel. So it didn't have enough fuel to stop and slow down when it got to Mars. So guess what happened? It went right by Mars. So NASA doesn't talk much about that screw up with accuracy in knowing imperial or metric, right? It was a, I bet you a lot of people lost their jobs over that one. If you get a chance, look it up. It's kind of a neat story about accuracy and about measurement, right? That how important it is. And we're talking really, really smart people can make very, very simple mistakes.
What's it called now? The story.
What's the what?
What's it called now that we should look up?
Oh, look up Mars, Mars mistake, kilometers and miles. That will probably get it under Google if you probably find it that way. If not, when we do our break, I'll try to find it for you.
Thanks.
You're welcome. Okay, so now again, we could then go on to circles. We can talk about perimeter, which is circumference, right? We can also talk about area. And area is kind of a neat thing. When you talk about the area of a circle, it's actually broken down into these pieces here. So area is pi r squared, right? And again, you don't have to memorize that. Now, the only thing you got to do is you got to know what r is. What's r as opposed to d? What's r?
Radius.
And if they give you the diameter, let's say the diameter is 10 centimeters, you realize with radius, you got to cut it in half, right?
Yeah.
Okay, so one of the neat experiments is, let's take a look at this one here. You got two pizzas. I know I'm going to tell you this story and you'll think, oh, what a math geek. I've actually figured this out because I did it one time when I was ordering pizza. I wanted to get the best value for my dollar, right? So I wanted to order the most pizza for the least amount of money. Maybe because I'm cheap. Maybe that's why. Okay. So you got a 14-inch pizza and you got a 10-inch pizza. So how much bigger is the larger pizza is what we want to know, right? So pizzas are measured by their diameters. So when we want to talk about doing anything with area, we have to talk about the radii, right? So radii is plural of radius, right? So the radii are 7 and 5, right? The 7 is the 14-inch pizza, the 5 is the 10-inch pizza. Same thickness, so it doesn't matter. So what we want to figure out is we want to figure out the area of each. So the larger pizza is pi times 7 squared, right? 7 squared is 49. And what is 49 times pi? Just so we have a size. Doesn't really matter. 49 times pi. 153 approximately. 153 square inches. The smaller pizza, 5 squared, which is 25 times pi. And if we want to find out how much bigger that pizza is, you take the larger pizza divided by the smaller pizza. So you could take the measurements or you could just leave them like this. What's going to happen to those pies? What's pi divided by pi? What's anything divided by itself?
1.
1. So they disappear. So technically you could do 49 divided by 25 and you find out it's 1.96. So what that means is you think about this, the smaller pizza is a 10-inch diameter. The larger pizza is a 14-inch diameter, but we have technically twice as much ingredients on that pizza. Right? That's what it means. So if you're going from 10 to 14, you get twice as many ingredients on that pizza. So then you can figure out price-wise, which is the better deal. I know it's silly, but I've actually calculated it out before.
This is vital information, Brian. I second this and I will support you, sir.
All right. What time is it? Oh, yeah. What do I got here? We're gonna do Pythagorean theorem right away, and then we can do some questions in a break in there. Okay. Pythagorean theorem. Sometimes you'll hear it as Pythagorean theorem. It's the same thing. It's just tomato, tomato. It just depends on how you say it, right? Pythagorean theorem was this guy, Pythagoras, and he came up with this really cool theorem. And you guys know this one already. It says that if you take a right, and this only works with a right angle triangle. If it doesn't have a box in that bottom corner, which this one doesn't, obviously. If it doesn't have that box in the corner, it's not a right angle triangle. It doesn't work. So what it is that he says that a squared, whatever a is, whatever the length of a is, plus b, whatever the length of b is squared, equals, and you add those together, equals c squared. It's standard form. We take it for granted. We use it all the time. Have you ever seen the proof? You ever seen actually where it comes from? Here's one of them. There's about 60 of them, I think. This is actually how it works. So a, in this case, when we take a squared, we're actually going a times a. We're finding the area of this side that's attached to that triangle. And b, we're finding the area of that side. And we take these two areas and add them together, we get the area of c, right? And that was actually one of the rules way back, I don't know how many slides ago, maybe 20 slides ago, when I told you, hang on, let me find it here. I'm just looking back through my slides, my pages. What rule was that? Addition property. Area R can be dissected into non-overlapping subregion is the area of the big one. So A and B have been dissected from C. If you add those together, you get the area of C. Okay. So, I mean, many of you have probably never seen that proof. Now, here's the deal. Some of you will not care about the proof. That's understandable. It's just there for knowledge sake. Here's the deal. Do you know how to use the formula? That's the more important thing. Okay, so let's look at one here. Oh, so then you can also prove if you actually take two triangles or two sides and square them and add them together, and you get the square of the longer side, you just proved that that's a right angle triangle. Okay, so let's do this question here. So here we go. We have a right angle triangle. We have two measurements, 13 and 37. Here's the question you have to ask yourself. Are you looking for the long side or one of the short sides? What are you looking for in this case? The
Long
Long
side.
side.
long side. And we often refer to the long side of the longest side of a triangle as the
Slope.
no,
Hypotenuse.
hypotenuse. Slope is rise over run. Hypotenuse. That's the other term we use all the time, the hypotenuse. Okay, so if we want to see what that hypotenuse is, we're going to take both these small numbers, right? Oops. We are going to square them. So 13 squared is 169, 37 squared is 1369. Add them together and then take the square root, right? So you end up with 39.2. And you know, remember, estimation is also a good thing, and knowing numbers is also a good thing. We know that this is the hypotenuse, this X value here. So that number, that answer should be bigger than 37 and 13. And it is, in this case, it's 39.2. Okay. Here's the question though. That's finding a longer side. What would you do if you're trying to find a shorter side? Oh, Lori, do you have a question?
Yes, I do. Okay, I have a question about how do you find the square root if you don't have a calculator?
You phone somebody that has a calculator.
Okay,
No,
that's
you,
what I.
you need. Now, there are ways to estimate something with a square root, right? But if you don't have a calculator, it's really, really hard to do. But let me just show you. Give me 1 sec here. 1 sec, 1 sec. Close this. Oh, hang on. I want this board. Give me 1 sec. This is how you estimate square roots, by the way. So let's say I wanted to find the square. Let's say I wanted to actually pick my pencil first. Here we go. There we go. Let's say I wanted to find the square root of 46, correct? Can't do that. Can't do that in my head. But watch. A number that's just lower than 36, or sorry, 46, it might be 36, right? What's the square root of 36? Anybody?
6.
6. And then I could do here, square root of 49. Ah, square root of 49. Square root of 49 is?
8, 9, 7.
7. Okay, here's the deal. Square root of 46 falls between 36 and 49, correct? So what's my approximate? What do you think it might be?
6.5.
6.5.
6.5
6
to 6 point, I don't know, 9, 8, whatever. Is there a range? Yeah, there's a range. So for instance, Lori, if you were really stuck and you didn't know, if you didn't have a square root of something, you could actually estimate it pretty easily by using something called benchmarks. That's what these things are. Okay.
Okay, thank you.
You're very welcome. That was a great question, by the way. Okay, where was I? Back here. Okay, here we go from current slide. Determine whether the three lengths given are the sides of a right triangle. Okay.
Brian,
Yes.
I have a question back on square root.
Yep.
So is there a way to manually, to manually square root something? Is there a process?
No, you'd have to estimate and then try to figure it out. Take a number, and multiply them together till you get that. Okay, do me a favor, figure that one out for 1 sec. I'll be right back. Figure out if that's a right angle triangle. Sorry about that. I'm drinking too much water. I had to go run to the washroom there. Okay, so determine whether the three lengths given are the lengths of the side of the right triangle. What are the two shorter sides?
15 and 8.
Okay, so 15 and 8. So if we were to do this properly, we would square 8, right? Square 15. And if it was a right angle triangle, they should equal 17 squared, right? So 8 squared plus 15 squared is 64 plus 225, which is 289. And is 289 17 squared? Let me double check here. 17 squared, 289. So based on that, the lengths are the sides of a right angle triangle. Now, some of you might, let's see if here's another trivia question. See if you know this. Most triangles, right, or end up kind of like this, where you end up with a decimal, right, like 39.2. There are some triangles out there that work out perfectly every time. For instance, can somebody give me an example of one? Well, there's one on the board right there. So if I had a triangle 8, 15, 17, that works out perfectly. When I say perfectly, I'm talking about no decimals, no anything like that. Can anybody give me another example of one?
Would doubling those numbers be another one?
it might be in that case, you'd have to check. Really, really common one is 3, 4, 5. Right? There's a bunch of them out there. Does anybody know what they're called? There's the trivia part. They actually have a fancy name. Not a big deal if you don't know. It's not going to be on the test or anything. They're called Pythagorean triples. That's what they're called because they're 3 numbers, no decimals, no anything. Okay. Okay, so that is, oh, actually, good thing after the break, after the next one is a shorter one. That was the longer part, 10-1 to 10-3. So what I got for you is we're going to do some work and take a break. So you decide how you want to do it. Do some questions, then take a break, or take a break now and do some questions. But we're going to get rolling again at 1:45. Okay. So that's just less than 30 minutes. So that gives you enough time to do questions and take your break, or take a break and do some questions. You decide. It's up to you. And again, for those that don't have it, I've posted the questions on the webpage. All right. I'm going to fix attendance because I think we had somebody join us. I don't know.
It was me.
No, I know. I got you down. It was after that. I think somebody joined us. I'm missing. Who am I missing? Christina, I think I'm missing, but she emailed me. Yeah, Christina, I'm missing. Kayla, did I get Kayla? Did Kayla join us? Kayla, you here? Kayla George, where is she? No, missing Kayla. And who's the other one? Brooke Mousseau. Brooke. Is there Brooke? Where's Brooke? No, Brooke. No, okay. That was the other one missing. All right. And what does Kyle say? So I'm applying pizza math every pizza purchase. Oh, that's good. That works, Kyle. I appreciate that. Gotta get your most bang for your buck. Kyle NASA be like, let's sweep it under the rug. That's a good one. Okay. All right, let me try to find that one. Let me try to find that article. NASA mission to Mars, mistake, KM and miles. I think that will do it. There it is. How NASA lost a spacecraft from a metric math mistake. There it is, right there.
Yeah, highly held organization would not want to talk about this, definitely.
So it was back in, when was it, 99? Oh, yeah.
Please share the link, please.
So what did it cost? 125 million.
Do you think they Urkeled it?
Yeah, it could be. So you see, yeah, the laboratory used millimeters and meters in its calculations, and then the Lockheed Martin, where they designed and built the spacecraft, was inches, pounds, and feet. I mean, it teaches you something. That would be a great one. Like if you're teaching kids about metric and imperial systems, of why it actually makes a difference and why it's really important. You can talk to them, but that's a real life example, right? Wow. All right, let me put this back up. Sorry. Oh man, I got a lot of, all right, might as well print all these assignments you guys just sent me. Oh, there it is there, okay.
Where do you share the link? On chat.
Yeah, give me a sec here. Print. I just gotta remember how to do this. Give me a sec here. Go back here. Go to this. How do I see? How do I change it to everybody here? To everyone. There we go. To everyone. Control V. There. That should be the link in chat then. That's cool. Let's print off this one here.
The break.
1 sec. Sorry, I just had to send an email. Sorry, what were you asking?
What's the expanded exponential form?
Oh, that's where you break it apart into something times 10 to the 4th plus something times 10 to the 3 plus something times 10 to the, like you work your way down through it. We did it on, hang on, I'll find you the actual page number we did that on. Give me 1 sec here. What was that again? What was the assignment? 7, 8, and 9, right? No. No. Hang on, let me find it here. Give me a second. I need to find the right one for you. Why can I not open this up? There it is. Shared. Actually, do you have your textbook?
Yeah.
Okay, I'll pull it on I'll show you what, I'll tell you exact page in the textbook. We go to the, we want, let's do it this way. Give me 1 sec. Just got to find the right page number for you. Exponential form, where is it? Let's do it an easier way. Let's go to this book and I can give you the exact page. is. Okay. Slide 7, 8. All right, and there it is there. If you have your textbook, you can go to 328. 328 is a really good example of how to do it. That one breaks the decimal down into a whole bunch of things. It's in that area there. It breaks it down into its powers of 10. Or actually, probably the best place. Let's start right at the beginning. Go to 325. And you'll be able to see the first example. 325 right at the bottom. It says in expanded form. You'll see it. Let me know when you find
Okay, I
it.
see that.
Oh, you see it? Yeah. So
Hey,
what you want to do is you don't want the bottom one. You want the one above it where it has like 2 times 10 to the 1, 3 times 10 to the 0, 4 times 10 to the -1. That's the form you can leave it in.
Like in multiplication.
Yeah, just you're basically breaking the decimal down into that or into whatever the number is into those pieces. You don't need the line below it with the 20 plus 3 plus 4 over 10. You don't need that one. You can use the one above it.
Brian.
Hang on one sec. Yeah, go ahead.
Is there a formula from grams to kilograms? Or should I?
Sorry, say that one more time, please.
For question 9 on page 502, is there a formula from grams
Hang
to
on,
kilograms?
502. Give me a sec. I don't have memorized, so I always gotta look them up. 502. Question.
9.
Well, how many grams are in a kilogram?
I don't really know. Or should I look it up? I thought it's in your notes.
Is it not on the formula sheet? Hang on. Hang on, let me look.
Oh, shucks, I forgot. Okay.
Hang on. We'll take a look here. What's today? Thursday, the 27th formula sheet. Oh, it has gram. There it is. Milligrams to grams and grams to kilograms. Yeah, it's right at the bottom of the first page.
Hey, thanks.
You're welcome. Farah, I sent you an email. Did you get that email, Farah? I don't know. Oh yeah, you're back here. Something didn't. I saw you sent in the assignment, but I can't print it off for some reason because I think it was sent as an email instead of. Did you use Genius Scan or did you just send it in? Because one of them looks like a picture. Can't really tell.
Yeah, no, I couldn't get, my internet is so slow at home right now. And I couldn't get my scan to work. So yeah.
Okay.
Screenshot it.
I will try. If I have issues tomorrow, I will email you and we'll figure out another way to send it. I should be able to do it if I change it to some other editor here. Yeah, I see, or you know what, I could just mark it in the email too. So.
Okay.
I'll give it a shot. I'll let you know tomorrow if I have issues. I sent you an email, but I wanted to talk to you first. So.
Okay. All right. Thank you.
Yeah, no problem. Okay, I will be right back, guys. I'm just gonna go pick up these print offs that I.
Hey, Brian.
Yeah.
I gotta head out. I not feeling too good. I'm coughing up a storm here. And I'll watch the video you post tomorrow.
You only need to watch the second part of it. Like we're in 5 minutes, we're gonna do 10-4 to 10-5. That's the only one you have to watch then, that part of it.
Yeah, I'm not feeling too good.
Okay.
All right, thanks, man.
Yeah.
Bye.
I have a question.
Yep, go ahead, Alice. No, you're muted.
Question 10A on page 503.
503.
I don't see it on your formula.
Which question?
10B. It's not on your formula sheet.
Oh, no, that won't be. You can look that one up. What it is there's a cubic meter of water. You think about it, that's quite a bit of water. How many kilograms does that actually weigh? You can look it up.
Okay, thanks.
No problem. The only ones that I put on the formula sheets are the ones you'll need for on the test. That one just happens to be an extra question on the in the book there. So there we go. Okay. Oh, I printed off these now. I need to send back telling the people I got them.
Would you be able to help me on an assignment?
Yeah, give me 1 sec here. Who was that? This was, that one goes over there. Okay, that one's done. Hang on, I'm trying to find my blank assignment here. Oh, I got too much stuff open here. And I want this one right here. Yeah, which question? Which question did you need help on? If you're talking, you might be muted, so.
Hello?
Hello, yeah, which question do you need help on?
Just hold on. I'm just looking for it. It was one of the last ones. Oh, number 25.
Number 25, okay. Let me take a look at it here. Okay, so what it is you have, hang on a sec, brand X. So what they're doing is they're saying brand X, which runs 55,500 copies, right? It runs 19% longer than their competitors, right? So their competitors are running less than 55,500. So what you got to do is you got to calculate whatever number, and I'm just throwing it out there. Let's say the competitor does 40,000 copies. Well, 40,000 copies times 19% added on, will that get you to 55,500? Well, no, 40,000 is a little bit too low, but you just got to do the math to figure out what the number is, that when you multiply it by 19% and add it on, you get 55,500. So you have to figure out how to go. So you have to figure out how to go backwards. If you're talking to me, you're muted. I don't know if you're. Did that make sense? We're past our time to actually get going here. Sorry, I was printing off stuff. Mary, I got that page. Thank you very much. It's awesome, that missing page. And I talked to Farah about that. Yeah, I'll print that off in a sec, or I'll try to print it off in a minute. Okay, let's get back and do this one here. Oops, that's the one we got from current slide. All right, make this smaller here. Okay, so we did up to 10.1, 10.2, and 10.3. All we're gonna do is volume in this case, and I just want you to have more practice on this stuff. Oh, and surface area, sorry, volume and surface area. And again, these are just formulas that are on the formula sheet. So again, you don't have to memorize these, you just gotta know how to use them. That's the main thing behind it, okay? So there's two we're gonna do here. We're gonna do surface area and volume. Okay, surface area is whatever three-dimensional shape we have, different than area, right? Because area is just two-dimensional. Surface area is a three-dimensional shape, and we want to talk about all the area that's on this thing. Volume measures what's in it. So volume would be length times width times height on a basic shape, right? Okay. So let's look at examples here. So the two we got are, first one here, the volume of this box. Okay. And it's a right prism, and then we're going to do right cylinder after that. So this one is 4 inches by 10 inches by 3 inches. So when we're dealing with volume, it's just a matter of using length times width times height. Now, the big thing is when we're dealing with multiplication, it really doesn't matter the order. So if you screwed up the order and did 4 times 10 times 3, or if you did 4 times 3 times 10, it's not going to make a big difference on a box like this. So length times width times height. What's that, Kyle? Oh yeah, okay, yeah, no problem, Kyle. So what we do is length times width times height. We end up 10 times 3 times 4, and we end up with 120 square inches. Now, there's a mistake on that slide. What's the mistake?
Isn't it exponent 3?
You got it. It's an exponent 3. I made a mistake. Well, I don't know if I made a mistake or not. So I'm gonna write myself a note so I fix that for next year when I teach this. That should be inches cubed, right? So put a 3 there if you can for me. Should say inches cubed because it's volume. You are correct. Okay, next one. Here's a cylinder. And a cylinder is basically, they'll give you certain things. Sometimes they'll give you the diameter, sometimes they'll give you the radius. In this case, the 5.5 is the diameter, so we're gonna have to cut it in half to get the radius. The formula, again, it's on that sheet too, pi times r squared times h. And r is just the radius and h is just the height. Now, don't be mistaken. This cylinder could be sitting on its side. Doesn't matter. Height is the overall length of it, right? So 2.75 is the radius. We square that, times it by pi, times it by 9.5. We end up with 225.7 cubic centimeters. That's volume. Okay. Basically, it's plugging the numbers into the formula. So basically how it works, this is kind of neat. And I call this the Pringles example here. Here's the interesting thing. Think about a can of Pringles, right? If you can, Pringles are not perfectly round, right? They have kind of they're oblong or whatever they are. So it's kind of like this shape here. If you can figure out the base, if you can figure out the area of one of those Pringles, all you do is multiply it by the number of Pringles in the can or the height, and you'll figure out the volume. It's really kind of a neat thing to do when you want to talk about volume, right? So really, I mean, you go back to this example here. If you were to find the area of just this cylinder, which is pi r squared right here, and then you multiply it by the height, of course, that's the volume. You take the area of the circle, multiply it by the height. It's the same with this. You find the area of the base, you multiply it by the height. Okay. These next formulas are just on your formula sheet. I'm just going to show them to you just so you can see. So something like this. Where is it here? I guess it's on the, I don't know why I put it. Oh, sometimes you'll see it this way. You'll see it as volume equals 1/3 capital B times H, or sometimes you'll see it as volume equals 1/3 B squared times H. The difference is the B squared, right, is the 8 times the 8 at the bottom here. The big B is the base, the area of the base, which is 8 times 8. So it really doesn't make any difference. You'll just sometimes see them differently as you're going through stuff. You'll see it as a capital B or a small b, but they are identical. Capital B means find the area of the bottom. B squared does the area for you. Okay, does that make sense? Hopefully it makes sense. Okay. Next one is area of a cone, sorry. Cone, well, that's a, woo, that pi r squared came out really weird on this one. This one is 1/3 times pi r squared h. So r is your radius, right? H is your, now look, h is your internal height. There is a difference. This outside line is called the slant height, which we use in surface area. But when we're doing volume, we do the internal one as that height, and then the radius. And there's your formula right there. And again, it's on the formula sheet.
I know why that's
Sorry, what was that?
I know why that's goofed up. It's not a font error. It's a input error.
Oh, like the way it
Someone
came out.
turned that into a gamma instead of a R.
Oh, that okay. That's what it is there. All right. Next one is a sphere.
I have a question.
Yes, Alice.
I was chewing food, so I couldn't ask you. What did you say what the big B meant?
Okay. Here, if you look, do you see how the bottom one is b squared?
Yeah.
So that means the base. So that's 8 times 8. Now, this one above it is the capital B is basically the b squared. So if you look at the previous one, whatever shape you have, right, like this weird shape, they refer to it as the big base, right? That's why it's a capital B. You just have to realize that if they ask you, if they say if they say capital B in there, it's the same as just finding the area of the base. So you can write yourself a little note right there. That big B, put a little line to it and say area of base, if that helps you.
Thanks.
You're welcome. Cylinder, 4/3 pi r cubed. So this one, the only thing you need is the radius of the sphere, and then you can figure out the volume. This would be like if you had a ball and you want to figure out the volume of air in it, whatever it is, or water, if you want to fill it full of water. Okay, so that's volume. Surface area, again, those formulas are on there. We're going to do 1, 3, 4 formulas here. And again, there's lots and lots and lots of formulas that probably not on there, which if you needed to look at. Okay, surface area. How I describe surface area, and this kids really struggle with this sometimes. Surface area is really quite easy. It's if I took a can of spray paint and I wanted to spray the outside of whatever shape I wanted to. Okay, so that is the surface area. So look at the first one here. If I have a prism shaped gift box, I have a box here. If I spray painted this, I'm actually going to paint 6 sides, right? I'm going to paint the left and the right side. I'm going to paint the top and the bottom, and I'm going to paint the front and the back. So that's where this formula comes into it, right? 2 times length times width. That'll give you the bottom and the top. 2 times length times height. That'll give you the front and the back. And 2 times height and width. That gives you the left and right hand side. Right? And that's for surface area. Now, if you wanted to, you don't have to use this formula. You could find the area of all 6 sides and then just add them together. Right? You could use a net. Remember we talked about nets 2 days ago. You could actually unfold the net, figure out the area of each piece, and then add them up. This is a simpler way. Okay. Next one is a cylinder. Here's the formula here. Surface area is 2 pi RH plus 2 pi r squared. Now, if you actually look at this, 2 pi r squared at the end here is actually the area of the circle on the top and the area of the circle on the bottom. And then this part here is if we unroll that whole outside rectangle, this is what you get from it. Okay. And again, you don't have to memorize the formula, you just got to know how to use it. Okay. Now, remember I said that on a cone, if it's an internal height, the H there, that was for volume. This one uses what's called a slant height, and it's the length of the outside here. So the formula again is SA equals pi r squared plus pi rs as, I don't know why there's a dot at the end. It's like, it's not a sentence. S is the slant height. So you need radius and slant height. And that's for surface area. Okay. Surface area of a sphere is 4 pi r squared. So you still need the radius, but you need the 4 pi r squared. And that'll get you the surface area. Okay, so then there's also something in here when you're dealing with this. You also have to talk about sometimes similarities or scale factors. In fact, I was just teaching this today to a grade 9 student, same concept. Scale factor is how much bigger something is or how much smaller something is. And we're talking here about like a photocopier. You have enlargements and you have a reduction, right? So the easiest way, if you're doing scale, and this is the dead set easiest way. So for instance, let's say, can you see my mouse on the screen? Let's say this bottom line is 10 centimeters long. Over here on S, this bottom line is 5 centimeters long. To find K, or the scale factor, all you do is you take the second measurement divided by the first measurement. So we end up with 10 divided by 5. So the scale factor is 2. So you could say this object on the right here is 2 times as large as the object on the left. Okay, and that works for enlargements and reductions, right? The only difference is if it's an enlargement, it'd be a number greater than 1. If it's a reduction, right, it's a number between 0 and 1. It's like a fraction, like 0.25 or a quarter or something like that. Okay, so wherever you see scale factor, second divided by first, and that applies to volume, area, all that stuff. Okay, that makes sense? Okay, so what that does is that gives us more time to work on questions, which is what I'm trying to get more and more of each time, because I know we're very limited by the amount of time we have for questions. So these ones here are 10-4 and 10-5. So these ones will be on, I want to double check to make sure I'm volume and surface area. So these questions, you're going to need your formula sheet in front of you, because you're going to have to look at the right formula for the right question. Remember, if it says volume, make sure you're looking at the V formulas. If it's surface area, make sure you're looking at the area or surface area formulas. Okay, and we'll work on this for about 20 minutes, I think.
There's a couple questions like this in the assignment number 5, like question 5 or 7, for example.
Wait, question on assignment 4. Hang on.
Assignment 5.
We're not even on 5. Hang on. Jeez, that's next week. Give me a sec.
Well, I mean, it's what we're doing right now.
I know. Assignment 5. Okay, which question?
5 or 7. I'm just wondering if you can do a quick example. It doesn't have to be like those exact numbers, just how to do the multiple thingies.
Here's the deal. If I gave you on question 5, if I gave you just the rectangle on the bottom, could you find the area of that?
Yes.
Right, 20 times 8. That's just the area of the rectangle on the bottom. The triangle that's on top of it, could you find the area of that? Do you have the base and the height?
Well, okay, that's, I guess, like the 14. Is that supposed to be the base or the height?
That's the height. Well, the base is 20 because it's the same as the one below it, right? So 20 is the height. So here's the question for you. What's that 17?
The hypotenuse, the longest side.
Do we even care about it in this question?
No.
No. Is it an extra piece of information?
Oh, that's what's throwing me off. That's what okay. Thank you. That's all I needed to know.
And then on 7, what you can do is you can cut that thing into pieces. Well, you actually don't need to. That's a trapezoid. Trapezoid is just the formula A and B and H. You have all 3.
Okay, perfect.
And are there any more? Let me look. Question 20. Look at 20.
Okay. Yeah.
Couple ways to do that. You could either consider the rectangle as a whole and cut out the circle, right? Which is probably the easiest. And you're actually not cutting out a whole circle, you're cutting out half a circle.
Okay.
So could you find the area of the whole rectangle to start with?
Yes.
Then could you know that the 3.6 is the diameter of the circle. Could you figure out the radius then?
Oh, I see. Yeah.
Sometimes there's information that's there to take away or add on parts.
So then I would just calculate like the full area of a circle times or divided by 2 and then take that out of the whole area.
You got it.
Okie dokie. Super. Thank you.
You're very welcome.
I have a question.
Yes.
Page 531, question 2.
531, question 2. Okay.
I still need help. So do I do C take away B equals A? Or C
Are you
take
talking
away
about 2A?
Yeah, C squared take away B squared.
Okay, so right, because you're finding a shorter side, you're going to subtract the sides instead of adding them, right? So you're going to do 2 squared, which is 4, right? You're going to do 1 squared, which is 1. So 4 subtract 1 is 3, but then you got to take the square root of it. So technically x is the square root of 3. And you can leave it as the square root of 3. You do not need to change it to a decimal. You can leave it as the square root of 3. That is a valid answer.
Okay. Thanks. So on my question, I would make a 3 with a square root.
Square root of 3. Square root symbol, right, which is called
Okay.
radicand, right? And then the 3 is underneath. Or radical, sorry, not radicand.
Okay, for question 3, do I use algebra?
So you still got to do the work, right? So you got to go x squared plus 2x in brackets squared, right? Equals 25 squared. And then you got to collect like terms and take the square root of it. So look, yeah, it's algebra, but you got to, the Pythagorean theorem is still the same, right? X squared plus 2x squared equals 25 squared.
Okay.
And I will be, try that one. I'll be right back. I'm just going to pick up the 3 more print offs that I just sent to the.
Hey, Brian, could you please help me out with 2B on page 540? I feel like there's a lot of numbers there and I don't know which one to get rid of.
2B on 5.
It's the volume of the prism.
Okay. So this is a good example of the Pringle thing I was talking about. Could you find the area of the trapezoid at the top?
Well, I don't know which numbers belong to what, to be honest with you.
The 10 is the base of the see the top trapezoid, right? That 5 is the height in the trapezoid.
Mm-hmm.
Oh, hey, so if you're looking at the formula for trapezoid, for area of a trapezoid, there's an A, B, and an H, correct? For area of a trapezoid.
To be honest with you, I'm kind of lost on that stuff.
Hang on, let me find it here. Area of a trapezoid right here. So there's A, B, and H. So if you look at the little picture, right, A is the top one, B is the bottom length, and H is the height. So according to that picture, 6 is the A, 5 is the H, and 10 is the B.
So, because I thought 7 would be the height.
No, hang on a second. I'm just, yeah, you can come in and clean, sorry. What it is think about this. Think about it, you're finding the area of a trapezoid and then you're stacking a bunch of trapezoids on top of each other. That's the 7 of the height when you want to change it to volume, right? Well, hey, let me explain it this way. Let me go back here, watch here. Let me go from current slide and back up. This is this concept right here. Right there, that one.
Mm-hmm.
You find the area of the base, right? Whatever that shape happens to be. In this case, it's a trapezoid, right? You find the area of that trapezoid, and then you multiply it by the height, and all of a sudden you get the volume. Okay? So if we're looking at these formulas here, right? If this is the area of a trapezoid, that's what it says. So the trapezoid's on the top there, right? So you got a 6, a 10, and a 5. Because that 10 on the bottom is the same as the 10 up above it, right? They just didn't write it on there. Hang on, you're not getting this. Let me throw it on the smartboard. I can tell right away.
I think I'm considering something different to be the base than you are, and that's where I'm, because I'm like looking, I'm like, well, it's 10 by 7. Like
10 by 7 is not the base. The 7 is the side.
But the base of the trapezoid is the square, right? So wouldn't that be 10 by?
No,
7?
here's the trapezoid. So I'm tilting it down. I'm tilting this trapezoid down. We're looking at it on that picture as an angle, right? Okay. So that one there is 6, right? And if you look, the 10 is from the left to the right. So that whole thing is 10 centimeters all the way across. Okay. And this here is 5 centimeters, right? Or 5 centimeters, sorry. That is the trapezoid itself. So when we want to find the area, right, we use the formula. That one right there. That's going to give me the area of that whole trapezoid. Now think about this. If you had a stack of trapezoids, you have 7 centimeters of a stack of trapezoids. You stack them on top of each other and they're 7 centimeters tall, right? So if you find the area just of that one, whatever that happens to be, and you times it by 7, you now have the volume is what you have. Let me get rid of that. You now have the volume.
Okay, but who decided we have to flip the trapezoid on that side? What if I want to keep it the way it is?
Okay, well, let me draw it differently then.
Because I'm just wondering, like, does that affect it? If I look at it, is it going to give me a different volume if I look at the numbers differently?
Well, the 7 has nothing to do with that trapezoid. That's just the height of it. Let me draw it this way.
But it says to find the volume.
I know, and I know.
Okay.
Okay, so that's 5 centimeters. That's 6 centimeters. That's your A. This is your H. In the formula, area. We're talking about area first. We haven't got to the volume yet. You have to put 2 formulas together to get the volume. Okay? I need B. I need that length right there. What is it?
I'm gonna be honest with you. What you're saying to me still doesn't make a lot of sense. I don't understand why you couldn't multiply it a different way. Like, why do you have to flip it back onto its base? Like that to me is where I'm not connecting the dots, I think.
Well, all I'm doing is trying to make, I'm just trying to find the trapezoid. It's a stack of trapezoids on top of each other, right?
Mm-hmm.
So if this is 10 centimeters down here, then that side length is also 10 centimeters, right? So if you ignore that, then ignore this whole thing for a minute. That shape right there is a trapezoid right there.
Okay.
So that's our 10. So could you find the area of that trapezoid?
Yes, I suppose so.
Okay, then what I'm gonna do is I'm gonna add another trapezoid right underneath it. Whoa, what the heck just happened there? Oh, I switched pages. No, or I deleted it, one of the two. What did I just do? Okay, so what I'm gonna do is right underneath it, I'm gonna add another trapezoid. So could I find the area? Why is it doing that? Could I find the area of that trapezoid? Yeah, use the formula again. And then could I add another trapezoid underneath? Could I find the area of that one? Yep, same formula. Could I add another one underneath that one? Yes. So what I'm doing is I'm adding a whole stack of trapezoids on top of each other. And how tall is that stack?
7, it says.
7 centimeters. So if I find the area of this one, and let's actually do the math, area equals 1/2, what was it, 6 plus 10 times 5. What's that, 6 times 10, 16, half of that is 8 times 5. So the area is 40, right? So the area of one trapezoid is 40. If I want to find the volume, all I do is take the area of that trapezoid, which is the big base, right? I just calculated the area of that big base and I multiply it by the height, right? It's a generic way of doing it. So volume in this case is 40 times 7, or 280 cubic centimeters. You can use that formula for any shape. So for instance, if I had a hexagon, you could find the area of the hexagon. And then if I had a bunch of hexagons stacked on top of each other, you could multiply it by the height and it would then tell you the volume, right? For instance, a can of Pringles. Think about a Pringle. Could I find the area of one of those circles of those Pringles? Yep, area equals pi r squared. And then if I stack the Pringles on top of each other, if I multiply it by the height, all of a sudden I have the volume.
Okay.
Just like that would be just a bunch of discs on top of each other, right?
Yeah.
I know it's a weird one to get your head around. Like it's well, because here's the deal: you're combining two formulas, right, instead of one.
Yeah.
You know, if the,
I have a question.
oh yeah, go ahead. You're muted.
It's
There you go.
question 3B.
Sorry, what?
At question 3B on the same page, is 7 the height?
3B. We're on 10.4. 3B.
Yes.
Yeah, 7's the height.
Okay, I just got confused because it's slanted.
No, it's slanted, but it doesn't make any difference, right? Like for when we did those examples with the here, let me show you just so you can see it here. Where was it? No, not that one. Hang on. Where were those questions we did in here? Hang on, I'm trying to find where they were. I'll find them real fast. These ones here, right? So it doesn't matter the shape, for instance, you have to look at what the height is overall, right? So even if there's a slant to them, kind of like this parallelogram, right? You have to look at the overall height, which is 12 in this case, right?
Okay, thanks.
You're welcome. Oh crap, I was sending, I got to email those people showing them that I got their stuff. Okay, I'll do that in a minute. Okay, so One last thing I want to show you, just so you have it, and this is for your reference. We were talking before about nets. I think we were talking yesterday about nets, right? Some people said they liked them. Some people said they had trouble with them, right? So what I've done here is I've included, well, let me talk about what I've included here. If you want to really explore with kids and you want to explore area and perimeter, there's a couple, I linked a website on here. So this one is square and rectangle. This is kind of cool. I'll just show you. So area, perimeter, exploration. So what it is you can pick things, right? So for instance, if I put a block on here, it's going to tell me what the perimeter is, right? And where is it? Area is 1 square units because it tells you it's 1 by 1. Now, what you can do is you can do this. This is really cool. You slap 2 of them together. So in this case, you can look at the perimeter, right? 2 plus 1 plus 2 plus 1, but it also shows you the area, right? 2 times 1, length times width. So it's 2 square units, right? So then you can do, that's a rectangle. You can add stuff to it. You can make it a square if you wanted to, right? 2 by 2 by 2, right? So the perimeter is 8. The square units is 4 because it's length times width. So it's kind of a neat little program if you're showing kids about it. And then you could, about area and perimeter, then you could also start showing them things like this, where you have weird shaped ones, right? So here's 4 and then 1, then 2, then 1, then 2, and then 2. Well, then you can show them that the perimeter is 12, right? And 6 square units, you'd have to show them that they're 2 separate things, right? There's this one and this one. 2 square units and 4 square units. And then when you stick them together, that's where you get your 6 square units, right? It's a really neat little program. So I'll leave, it's always going to be on the website. That never is going to go down. The other one I was going to show you is you can also talk about with area and perimeter. We talked about this 2 days ago, that geo sketch one, right? This one, you can actually use it to show area and perimeter, right? So you could draw your shapes. Oops, draw your shapes. Sorry, I forgot to put the elastic band there, right? Draw your shapes and whatever it was, and then get them to calculate the area and the perimeter based on that. Another good one. Now, the last one here is nets. So here is a website with printable nets on it, and these are really nice ones. So this one gives you 7 different shapes, right? And you can see, so here's the shapes here. So all you do is you could give these to kids. They could cut them out. Now, these little weird shapes on the edges are the tabs, right? So you fold along the dotted lines and then you glue the tabs together or tape them, and then you get really, really good, really, really nice shapes, right? So you got a cube, a square pyramid, square bottom pyramid, right? A rectangular prism, a triangular prism, right? Which has triangles on the ends. And again, you could unfold them to show them area, right? A triangular pyramid, you can unfold it to show them area. Because a triangular pyramid is basically, once you find the area of 1, you just multiply it by 4. And a cylinder, right? You can show them that one. And what was the last one? That one's kind of cool. A hexagonal prism. Okay. I just wanted to show you that. So those are on there for you guys to use if you ever need them. You might want to print some of this stuff up and throw it in a binder. So for when you actually teach that unit, or like where it says printable nets. Oh, no, that'll be fine. Where was it? Like websites like, where is it? Squares and Rectangles. You can see it's this toy theater. You might want to write that website down. Okay. Okay. Well, if you have questions, I'm sticking around. I'm not going anywhere because I got to print off some stuff here. So I'm gonna hit pause, or sorry, I'm gonna hit stop on the recording, and then you can ask me questions if you have. Okay, give me 1 sec here. Stop sharing.